Okay, so the confidence interval for the population mean. What's going on here? We have a sample x from some unknown population, and we want to know the population mean. So if you compute the sample mean, this gives you an estimate for the population mean. But now we don't want just a number, we want the whole range. So we need to know, take build the sampling distribution of the mean, and then cut off these bottom and top and bottom quantiles. All right. From the previous section, we know that t distribution is the best model for the sampling distribution of the mean. Okay. And this is the pivotal transformation that, here you have custom at location here and scale this. If you do this, subtract the mean and divide by the standard error, then it becomes the standard norm. Location 0, scale 1. Okay? And so when we build confidence interval for the mean, we're going to use the t distribution, and we're going to cut off the bottom alpha over 2 and the top alpha over 2. So here is the number. So this is a number, and this is a number that describe this location here. Where do we need to cut to obtain 1 minus alpha of the distribution in the middle? All right. So note, this is a positive number because we're in the cutoff is positive. We saw it actually. It was 1.94. Whereas the bottom, so the fifth percentile is a negative number, right? It's on the left here. So this will be important to keep in mind. This is a negative number, this is a positive number. Okay. So what do we know is that the t distribution between the lower and the upper quantile contains 1 minus alpha. So every time I say 1 minus alpha, just replace it by 90%. You just want to make it general, but yeah, think 90%. Okay, but now we have a problem, and this is one of the main new ideas, probably the only new idea in this whole section. In section 3.1, we learn about sampling distribution. Given the known population parameter, like the mean, the sampling distribution told us the possible sample means we can obtain, right? So it's assuming the population mean is known, what are the type of sample means we can observe? We're interested in the inverse problem. We have observed a sample mean, so right, in a practical statistical analysis, you don't know the population mean. Instead, you have one sample mean, and you want to know, well, what is the population mean that generated this sample mean? Okay, so it's the inverse problem. But no problem, we can, right, so the variability, the t distribution describes the variability of the difference between the sample mean and the population mean. So in these few math steps, I'm going to explain to you in words, you can look at the math later. What we're doing is flipping the distribution. So we take, we know the variability of the sample means with respect to the population mean. Now we're just thinking of it backwards. We're given a sample mean, where is the population mean? Give me an interval where the population mean could be. So this is how we do this. We start with the pivotal quantity and the two quantiles of the t distribution. We perform some analytical steps, but each of these steps preserves the probability event. So the description inside the curly braces doesn't change. We're just doing math and manual manipulations. So by the end of this, this interval still contains 90%, so 1 minus half of the probability. Okay, so let's look at it a little bit more closely. So this event, we're just gonna extract it, the limits of it. So if you take the sample mean, and this is, remember, a number like minus 1.6, some number, some multiple, but a negative number. If you go to the left of the sample mean by this many standard errors, and the upper limit, you take the sample mean and you go a few standard errors to the right. So this interval, the way we constructed it, will contain 90% of the probability. Okay, so this is this is how we construct confidence intervals. Basically, we find a range of numbers that, because of our model of the variability of the samples, we know this range of numbers contains the probability that like, will be correctly capture the unknown population mean 90% of the time. Okay. Note, the probability statement is made with a capital CI. So this is capital X means for a random sample, for a random, the standard error computed from a random sample, and so on and so forth. In practice, the formula you're going to use is applied on a particular sample and particular standard error. This procedure, the way you use this procedure, will sometimes work and sometimes fail. You know, for a given sample, remember the graph? So this is the procedure, and 4 out of these 50 times the procedure failed. The only thing we can say is that the procedure described in this box succeeds with probability 1 minus half. Very important distinction that for one particular sample, there's nothing you can say. Well, you know that you use the procedure that succeeds 90%, but one particular sample, it can either work or fail. Like this one failed, this one worked. Okay, so I know this is a little tricky, but that's what we get. Okay, so let's look at an example. We have Apple's dataset, which contains how many? 30 observations. So we have a sample size 30 from an apple orchard. So these are the weights in grams of 30 apples picked randomly from this year's batch. Okay. We want to know what is obtain a 90% confidence for the population mean. So what is the average apple size, apple weight? You know, if you look at here, you see it's, you know, let's compute the sample. A bar is the mean of the sample. So roughly, I think the apples are roughly 200 grams on average. But you know, it's much more interesting to know a confidence interval. Okay, so we're just gonna apply the formula. Let's look at it. Okay, so first we need to know the sample size, because the degrees of freedom of the t-distribution is n minus 1. So you need to know that. Compute the sample mean. Right, A bar, like I always say, and the standard error. Well, let's look at the formula. So you need the sample mean, the quantiles of the t-distribution, we're going to do that in a second, and the standard error. Remember, the standard error is standard deviation divided by square root of n. So that's exactly what we're computing here. Okay, and I'm just printing these numbers so we see what's going on. Okay, so now we need a t-distribution with n minus 1 degrees of freedom. Right, the sample size n, so we need n minus 1, so with 29 degrees of freedom. And then once we have the t-distribution, we want to find the location of the lowest 5% quantile and the upper 5% quantile. And then we just plug in the numbers. So here is the formula, x plus the lowest quantile times the standard error, and the same thing for the 95th percent. So this number, this range, is much more interesting. So here we had a point estimate, we just said a number, and now we have an interval. Really, the population mean could be anywhere between 196 and 208. So this tells us not only where the mean is, the population, but really based on the uncertainty of our samples, we believe the population mean is somewhere between here and here. So this is what you want to know. As an apple orchard producer, the mean is good. I mean, we want to know what the population, like a single number, but we really want to know the uncertainty. You know, what would be higher or lower? What's the highest population mean? Is roughly like, it's not higher than that, or it could be, but very small probability. And what is the lowest population mean? It's 196. Could be even lower, but unlikely. Okay, so that's more useful. Note, by the way, if you were to obtain a larger sample, the confidence intervals, so the standard error, right, depends on the square root of n. So the larger samples you get, the less variability. So the confidence interval will shrink, will get more and more precise. Okay? Make sense? Make sense? Okay, let's do that again. So this whole procedure was using the formula, the analytical formula. A lot of math. I mean, not that much math, but still. But here is the bootstrap procedure. It's 2 lines of code. I want to know the sampling distribution, a bootstrap distribution for the sample means generated from the single sample. We have only one sample. We generate the bootstrap distribution. So this list here contains a lot of, like 10,000 simulations of the sample mean. And then once I have that, I just cut off the bottom 5% and the top 5% from that distribution. Let me show you that. Hist plot. So this is the possible sample, the sampling distribution, the bootstrap distribution for the sample mean. You see, it has quite a bit of variability. You know, these are the real sample means we can expect. And by cutting off the bottom 5%, somewhere here, 97, and the top 5%, we end up with this confidence interval. And this will happen, you know, like, it's important to think that all these formulas and the numerical simulation, they're not perfect. Like there's variability in the samples, there's noise. So don't report this number. This is what I would report. It would be 97 to 208. You know, don't look at the numbers after the decimal. Just because the math can report, really, it's not that precise. And same here, you see, like if you round things up, the bootstrap confidence interval and analytical formula, they give you the same answer. Okay, so this is good. Anytime you can, when you're learning a new topic, it's good to have at least 2 ways to compute some quantity. You know, then you know what's going on. Otherwise, if you just memorize one formula, like so in a normal statistics class, they would just show this formula and be like, this is how you compute confidence intervals. But I want you to know the math formula way and the bootstrap, so the computational approach. And you can, so if for people who are programmers, here is a summary. This code block contains all the steps we did until now, in a reusable as a reusable function. So you give it a sample, you tell the error level, and choose a method. So method can be A for analytical or B for bootstrap, and it will do the steps. I'm not going to read the code for you, but yeah, it's just a concise summary of all the steps we did above. What I will show you, maybe I should run this, is a simulation. So let's run 100 simulations. You know what? Let's do 1,000. For samples of size 20, so here is a population. To run when I'm running the simulation, I can invent a theoretical population. This is the kombucha distribution. I'm gonna generate samples of size 20, and then compute an analytical confidence interval. Right, so just calling the function with the method. So this will get the t-distribution, this will compute the mean, the standard, it does all those steps, and a bootstrap confidence interval. So the same function, but using method B. And for each of those, if the confidence interval, the population mean is inside the confidence interval, I'm just going to increment the counter. So this is the count of successes for the analytical approximation method, and this is the count of successes for the bootstrap. This might take some time, but this is another principle I want you to take away from. If I teach you anything about statistics, is always verify. So there's a bunch of formulas, there's computational procedures, but trust but verify. So now we're doing a real simulation, see how many of the confidence intervals are really capture the mean, and how many of these capture the mean. So I don't know how it's taking so long. Okay. Next video will be on the population variance. Anyway, I'll tell you the numbers because I've run this before. For the analytical methods, we're gonna get roughly 90%, and for the bootstrap, we're gonna get a little bit below 90%. So we promised that procedure will work 90% of the time, but it only works 87.6. You know what? Close enough. You must agree. Okay. Because I'm recording video, this will take too long. So you'll have to trust me that these are the numbers. All right. See you in the next video. We'll talk about confidence interval for the variance.